And action.
Okay, so today we're analyzing the motion of a particle from an acceleration versus time graph using the idea that the integral of acceleration equals the particle's velocity, and then also using the idea that the integral of the velocity equals the graph's position. Boom.
Hi, so to find the velocity time graph by using an acceleration graph, acceleration time graph, you have to find the area under the curve of the acceleration. So to do that, we're going to do this in seconds. So this is going to be our first second. And in our first second, we're going to find the area under the curve of our acceleration graph. So it's just this part. We'll call this area 1. And area 1 is a rectangle. So that's 6 and then 6 down and then 1 to the right. So 6 times 1. And it is a negative, it's negative acceleration, so it's going to be a slope downward. So that is going to be, we're starting at initial velocity of 8 and going down 6 to 2. All right. So in our first to second second, there is no acceleration, so you're going to have a constant velocity, which is just noted by a straight line. And so we'll just put that nice little line here. And then in our second to third second, second to third, you're going to have a nice little rectangle. So this is going to be A2, and A2 again is going to be 4 to 0, so that's 4, and then 2 to 3 times 1. So that's an area of 4, and since it's positive, you're going to go from 2 to 6, 2 plus 4 is 6, and draw a nice little line. And that is the first 3 seconds.
In order to find how much our velocity changed from third to fourth second, we have to find the area under the curve on the graph of acceleration versus time. So this area can be divided by half, and we can find the overall area by adding this area with this area. Let's call this area area 3. Area 3 is the area of a triangle with a width of 1 and height of 2. So to find it, we multiply 1 by 2 and divide it by 2, and it's equal 1. Let's call this area area 4. The area of 4 is equal 1 multiplied by 2, and it's equal 1. So the overall area is going to be equal 3. From second 3 to second 4, our velocity increased on 3. So we add 3 to 6 and we get 9. And this is our velocity at 4 seconds. Then, to find the value of velocity on 5th second, we find the area under the curve from 4th to 5 seconds. Let's call it area 5. Area 5 is the area of a triangle with a width of 1 and a height of 2. So area 5 is equal 1 multiplied by 2 and divided by 2, and it's equal 1. So from second 4 to second 5, our velocity increased on 1. We added to our initial value 9 and we get 10. We can't connect these points using diagonal lines anymore because our acceleration was not constant. So that means that our graph is going to be drawn smooth, and this graph represents derivative of this graph, which means that as this graph is decreasing, this graph is going to be concave down. And just to check if our graph is accurate or not, if we draw a tangent line here and tangent line here, this is going to be more steep than this one, and it's going to be more flat than this one, which means that the value of acceleration at this point is going to be lower than the value of acceleration at that point. And that's right, so our graph is accurate.
All right, so for our position chart, from position according to our versus time, we have our starting position of negative 10 centimeters. And so we have start at negative 10, and we actually look to our velocity to find how much our position changes. So from 0 seconds to 1 second, it changes by 5, because right here we have a triangle, okay, and a rectangle. So the triangle has a height of 6 and a length of 2. So this area will be 3. And the rectangle has a width of 1 and a height of 2. So its area will be 2. So 3 plus 2 is 5. It increases by 5. And from 1 to 2 seconds, it increases by 2. For the same reason, area under our velocity thing, width of 1, height of 2, is 2. So it goes from negative 5 to negative 3. And then, from 2 seconds to 3 seconds, it increases by 4. Similar to from 0 to 1 seconds, we have our triangle plus our rectangle. So triangle has height of 2, width of 1, so its area is 1. And wait, 6, 4. Oh, has a height of 4, width of 1. So area is 2. Width of 1, height of 1. Height of 2, area is 2. So 2 plus 2 is 4. So negative 3 plus 4 is 1. So this is where our values get a little bit more tricky. So at 4 seconds we have 8 1/3. At 5 seconds we have 8 2/3. So this is figured out by actually figuring out the equation for this line in the acceleration chart. So in the acceleration chart we figure out that, alright, so this point right here, that's at 3 seconds, 4 meters per second squared. So x is 3, y is 4. And slope is negative 2. Alright, so right there we already have our negative 2x in our, so if we do the equation where y is equal to mx plus b, where b is our y-intercept and m is our slope, we already have our negative 2x. All we need to find now is our y-intercept. So what we do is we can keep on drawing the line, and if our graph still extended, we would find out that this line will extend and hit at 10 meters per second on the acceleration. So that would be negative 2 plus 10. So meters per second squared. So this is our acceleration from 3 to 5 seconds, not anywhere else. So velocity is the integral of our acceleration. So it would be negative x squared. Because of integrals, we would divide by 2 and add the 2 up here, and plus 10x. We would also have to do the plus c. So we would figure out our plus c by plugging this equation into our velocity. So we would do it at, I did it at 3 seconds, and so you would do something like, so a velocity of 6 is equal to negative 3 squared plus 10 times 3 plus c. Alright, so what we end up getting is, I'm not going to show you all the algebra, we end up having c equal to negative 15. Right? So in our velocity, we have negative x squared plus 10x minus 15. Alright? So then we have to find the integral of our velocity. Here I will rewrite it on our position graph. So our velocity is negative x squared So then we would find the integral of this to get position. So same thing, what we do is we go, so x is equal to, or x is equal to negative 1/3 x cubed, because of integrals, plus 5x squared minus 15x, and then again plus c. So this time we plug it in for our position graph. So at 3 seconds we have 1 meter or 1 meter. So we would have 1 is equal to a 1/3 times 3/3 plus 5 times 3 squared minus 15 times 3 plus c. And we end up having c is equal to 10. All right. So now we have our equation for this line. So we have x is equal to negative, or position is equal to negative 1/3 x cubed plus 5x squared minus 15x plus 10. If we plug in 4 for x, we would get 8 1/3. If we plug in 5 for x, we would get 18 2/3. So,
Go.
all right, so the reason why it's concave down or curved down here and curved up here is we have to look to our velocity chart. So from 0 to 1 seconds, our velocity is decreasing. So although our velocity is still positive, it's decreasing, so this isn't going as fast anymore, so our line will curve down. And from 1 to 2 seconds, we have constant velocity. So straight line here, and so it's increasing constantly, so we have a straight line from 1 to 2 seconds. And from 2 to 5 seconds, we have it curved up, because from 2 to 5 seconds on our velocity, it's increasing. So our position will increase more and more because our velocity is increasing more and more.